Hello and welcome back. So we'll continue with the ulangan paper of STPM 2019, section B. Question 16, we have a point charge of positive 2 microcoulomb move into a region of uniform electric field with a constant velocity. So electric field is established between two plates A and B, which are connected to positive 5 and negative 5 potential terminal. The distance between the plates is 3 centimeter. First is to describe the path of the point charge which moves through the electric field. So this is what we have learned before. When there's a potential difference between the plates, there will be an electric field flowing from the A to B. So when there's a moving charge moving across the plates, so there's a electrostatic force which is downward directions, since the positive charge will be repelled by the positive plate and attracted to the negative plate. So this electrostatic force will cause the point charge to accelerate in downward direction while moving to the right with a constant velocity. In the end, point charge will move in a parabolic motion. So we move to the next question, B. So calculate the electric field between the plates. So straightforward, we just use the formula of E is equal to V over D, where the V is the potential difference between plate A and B. So we have positive 5 and negative 5. So the potential difference is equal to 5 minus negative 5, which is equal to 10, divided by the distance 3 centimeter or 0.03 meter. So what we have is 10 divided by 0.03, and you will get 333 watt per meter. Okay, so move to the next one. Determine the magnitude of the force experienced by the charge. So we have formula of force is equal to QE, and the charge is positive 2 microcoulomb multiply E. So E multiplied 2 micro. And you will get 6.67 times 10 to the power of negative 4. Newton. Okay, so simple. So we move to the next question, 17. So this question has been discussed in one of my video, which is about the Hall voltage. So you can refer back to the video. And for here, we would answer the question on describe how the Hall voltage is produced. So you need to remember the phenomenon, how it is happening. So when there's a current flowing through this semiconductor, we learn that there's an electron flow through the semiconductor, and we have a magnetic field. Okay, according to the questions, it is perpendicular in a uniform magnetic field. So you have a moving charge and you have a magnetic field. So we have the magnetic force applied on the moving charge. So it is about the Fleming left-hand rule. So when you apply your left hand, okay, so electron will move in this direction, okay, for the electron flow. So it is push upwards and cause the upper surface to be negatively charged and induce a positive charge on the lower surface. So this potential difference between the upper and the lower surface is known as the Hall voltage that provide electrostatic force on the electron. Okay, so this is what happened. So we have the magnetic force upward, and when you have negative, positive, so you will have a downward electrostatic force that in the end, electron able to move in a horizontal, moving across the semiconductor. So this is the overall phenomenon of the Hall voltage. So for the next two questions about the drift velocity and density of free electron, you can refer back to my video, and this is the solution. The link will be provided in the description below. Proceed to section C, question 18. So question A and B is about the dielectric material and also the process of charging of a capacitor, which is similar as the question in STPM 2019. So you also can watch back the video if you haven't do so, and we will skip these two questions and proceed to question C. So we have two capacitors of capacitance 10 microfarad and 50 microfarad are connected in parallel and charged by a supply of 120 watt when the switch S is closed. S is then open and both capacitors are allowed to discharge through a resistor of 500 kilo ohm Determine the time taken for the potential difference across both capacitor to decrease to 10 watt. So this is about the discharging of capacitor. So before that, let us determine the equivalent capacitance of these two capacitors in parallel. So the formula to calculate the capacitance in parallel is the same as the formula to calculate the resistance in series as what we have discussed. So the capacitance is equal to 10 plus 50 equal to 60 microfarad. Simple. And for the potential difference across the capacitor, or the initial potential difference, it is charged by a supply of 120 watt, so it should be equal to 120 watt. Okay, so this would be the initial potential difference. And as for the time constant, so we learned that it is equal to RC, and we have the resistance of 500 kilo multiply the 60 micro. So we have kilo and micro, so 500 kilo multiply 60 micro. And you have 30 seconds. So now we have all the information ready. We have the voltage required, 10 watt. V0 is 120 watt, and also the time constant, 30 seconds. So now we can determine the time taken. Okay, so we want to have 10 watt from the 120 watt. So multiply e to the power of negative t over RC. Okay, 30 seconds. So we just solve this one as what we have solving before. 10 divided by 120. And then we apply ln. And then we multiply negative 30. So you can do it on your own pass, but this will be the answer that the t is equal to 74.5 seconds. Okay, so we proceed to the next question. If both capacitors are connected in series, calculate the required potential difference across both capacitors with the same amount of energy. So we need to maintain the energy. So energy is equal to half CV square or half QV or half Q square over C. So you need to choose the formula, but also we will calculate the equivalent capacitance first. So in series, so what we do is just the reciprocal of 1 over 10 micro plus 1 over 50 micro reciprocal. Because this is how we calculate the equivalent capacitance of capacitor in series. So 1 over 10 plus 1 over 50, and then we do reciprocal. So it is equal to 8.33 microfarad. Okay, so I think we should choose the half CV square. So because that we have a different capacitance, and we need to find the potential difference, and so we have to use the half CV square instead of the other two formula. So we need to maintain the energy. So the energy should be the same. E is equal to E. Okay, so what we have is half CV square is equal to half CV square, half C1 V1 square equal to half C2 V2 square. So the half can be cancelled. So the first C1 is 60 microfarad. Multiply the voltage, which is 120 watt, equal to the new capacitance, 8.33 micro, multiply the voltage square. So this is how we can solve these questions and obtain the new required potential to maintain the same amount of energy. So we have 60 divided by 120, multiply 120, divide by 8.33, and then we square root the answer, and so the voltage is equal to 29.4 watt. Okay, so this is the new voltage required so that it has the same amount of energy as the previous connection. So this is for the capacitor. So we move to question 19. We have the inductor of 0.2 Henry with negligible resistance is connected in series with a resistor of 9 ohm, a battery and a switch. So battery is 1.5 volt and has an internal resistance of 1 ohm. Explain the phenomenon of self-induction. So let's revise about this phenomenon. So it is a phenomenon of induced EMF in the conductor when there's change in current flowing in the inductor itself. So this is the keyword for the self-induction, inductor itself. So when the current changes, so magnetic flux linkage is also changing. So based on the Faraday's law, there will be an induced EMF, which is known as the back EMF for this case of inductor to oppose the change in magnetic flux. So you need to remember how to explain the phenomenon. So, and then we proceed to the question 2. Calculate the rate of change of current when the current is 0.1 ampere. So we can use the formula V is equal to negative L di dt, but you need to be careful that the voltage here is actually referred to the voltage across the inductor. So if you use the voltage of 1.5 volt, you would fall into the trap of these questions. So you need to find the voltage across the inductor first before you can apply the formula. And you can see that they provide you the resistance. So you need to do your own thinking how we can solve these questions. So for this one, what is we can do is that you can just straight away to have the 1.5 volt. Okay, so if you apply the control voltage law, what we do is 1.5 volt just minus the voltage across these two resistors, and the remaining voltage it is equal to the voltage across the inductor. So what we do is just we have the 1.5 volt multiply the voltage across these two resistors, which we have the current of 0.1 ampere multiply 1 plus 9 ohm, and this is the voltage across the inductor. And then now we can apply the formula. It is equal to negative, we can remove the negative sign. So we have the inductance of 0.2 Henry multiplied d I dt. Okay, I hope it is not too fast. So what we do is just to solve these equations. So 1.5 minus, so this would be equal to 1 divided by 0.2. And you have the rate of change of current as 2.5 ampere. So the negative sign here is actually important when you do the derivations, but it is only for you to identify the direction of the voltage or maybe to determine the change of current either is increasing or decreasing. So for here, we don't know the actual situations that is either increasing or decreasing. So it is safe to remove the negative sign and leave the answer as 2.5 ampere in these questions. So we proceed to question B. So this question also has been discussed in one of my video, which is about the mutual inductance. So we just quickly read through the questions. So we have these parameters, and when the current in P changes, pointer in galvanometer connected to Q is deflected. So explain the phenomenon observed, okay, in Q. So you need to explain the observation. So here you could see that there's a deflection in galvanometer. So you should know there is an induced EMF in coil Q. So it happens between two coils. So this should be the phenomenon of mutual inductance. So now we're just going to repeat almost the same explanation as what we did in the self-inductance. When we have the current in P changes, there's change in magnetic field linked to coil Q. So there's an induced EMF with coil Q that obeys the Faraday's law. So this phenomenon is also known as the mutual inductance. So you need to be sure what is the difference between the self-inductance or the mutual inductance. If not, you can watch back the video about the mutual inductance that I have also provided the solutions of question 2 as shown in this diagram. So we just proceed to the next question. Question 20. So the waveform of a sinusoidal voltage which is supplied to a resistor. So sketch on the same axis for the current and the instantaneous power. And then if the resistor is replaced by the inductor, sketch on the same axis on another graph curve of the current and also the instantaneous power. So we have two graphs need to be sketched. First is for the resistor, and second is for the inductor. So this is about a pure resistor and a pure inductor circuit. So has been discussed before. So this is the graph. So just roughly explain about it. So for a pure resistive circuit, you should know that the current is in phase with the voltage. So when you apply when you recall back the formula of the power, it is the sine square, and you would have this kind of graph that power is always positive all the time, which indicates that power is always dissipated as heat energy. And as for the inductor, so for the current, it is 90-degree leading the voltage. So you could see that the voltage is on the left, okay, compared to the current. So this is when the voltage is leading the current. And as for the power dissipation, you could see that it's alternating between the negative and the positive value. So this means that we have a zero average power dissipation across the inductor. So the phenomenon for the inductor is almost the same as what we can observe for a capacitor, except that the voltage of the capacitor is lagging behind by 90 degrees. Okay, so the graph is quite straightforward. If not, you can watch back the video and revise on the graph. So we proceed to the next question. A bulb labeled 120 watt, 60 watt is connected in series with a resistor and an alternating current of root mean square voltage 230 watt and frequency 50 Hz. Determine the value of R so that the bulb glows with normal brightness. So a bulb is considered as a resistor, and we have a purely resistive circuit. So to determine the value of R so that the bulb glows with normal brightness, it means that we supply 130 watt to the bulb and also 60 watt. Okay, so which means that the current across the bulb should be equal to 60 divided by 120. Okay, we have the formula of power equal to VI. So the current is equal to the power 60 divided by 120, and it is equal to 0.5 ampere. So this is the spec that we need to supply to the bulb so that it can glow with normal brightness. So to determine the value of R, what we do is we can apply the V equal to IR, that the current should be 0.5 ampere. So we have 120 volts supplied to the bulb. So the remaining voltage should be supplied to the resistor. So the voltage across the resistor R is 230 minus 120. And the current, so they are in series. So the current is also the same, 0.5 ampere multiply the resistance. So we have 230 minus 120 is 110, divided by 0.5. And you would have the resistance of R as 220 ohm. So quite easy, and it is quite difference with the schema. So you can compare, and you can actually think how we can solve these questions. So proceed to the second question. If R is replaced by inductor, determine the self-inductance so that the bulb glows with the same normal brightness. So you can consider this as RL circuit. So what we have is that we have the phasor diagram we learned before. So which we have the voltage across the resistor and also the voltage across the inductor. So like what we did just now, we just straight away get the difference between the voltage to obtain the voltage across the resistor. But for RL circuit, we cannot do the same method. We need to apply the Pythagoras theorem, that we have the formula of the V square is equal to the voltage across the resistor square plus the voltage across the inductor square. So besides the formula that is used in the schema, so here I will introduce you another way to solve this question, that we just need to care about the voltage. So we can use the formula of the voltage is equal to I multiply the reactance. So what we need to do here is we can find out the voltage across the inductor by using this formula. Okay, this is only applied for the RL circuit. So to do that, what we have is we just use the square root of the voltage applied 230 square minus the voltage across the resistor. So we still need to have a 0.5 ampere multiply the reactance of this inductor. So reactance is equal to 2 pi f, 2 pi multiply 50 hertz, as in given in the question, multiply the inductance. So this is how we can apply this formula to solve this question. So what we have is square root of 230 square minus 120 square. And then what we do is divide by 0.5 ampere, divide by 2 pi, divide by 50. In the end, you can get the inductance as 1.25 Henry as the same in the answer schema question. So if you think my method is simple, easy to understand, you can let me know in the comment section. And then we're going to move to the last question of this paper, state whether a resistor or an inductor is more suitable to be used to regulate the current. Justify your answer. So comparing resistor and inductor, so like I mentioned in the previously, so if you use a resistor, there is a power dissipation as heat energy. But if you use the inductor, average power dissipation is equal to 0, means there is no energy loss. So I would suggest that inductor is more suitable than resistor because we can save more energy. So this is all for the STPM 2019 ulangan paper. I hope you do enjoy the explanations and hope to see you again. Thank you for watching.